Alright, let's start. So, yeah, we were discussing the condition number. Condition number of a matrix when considering this matrix times vector as our function. So x is our input, and our output is ax, and then this condition number, is defined as this the relative relative condition number, which is the ratio between the two relative changes between the input and the output, and through some inequality called the Cauchy-Schwarz inequality. And so we were able to derive it, or this condition number or relative condition number, as the ratio between the maximum and the minimum singular value of a given matrix. So in general, your matrix, when it is used as a multiplier with some vector or any other matrix, and then largest, the gap between the largest and the smallest singular values are small, and then it's more desirable or preferable. Okay, so we can think of this condition number in the context of a linear system. So let's think of the linear system of ax equals b. Okay, so in this case, what is the input and output? So input is a and b, right? And then we want to obtain so given this a and b as our input, we want to obtain the x value over here. So in this case, we can view a and b as our input, and x, which is the solution of this linear system, as our output, right? And in general, if A is a square and a singular matrix, and then also between these two inputs of A and B, and then if we consider B as a constant, and then it can be viewed as the function of A, and still the output is x. And then if A is a singular non-singular matrix, and then the solution can be represented as this. Okay, so here we can also think of this relative condition number in this particular case, where the input is A and the output is x. So the relative, by the definition, the relative condition number is defined as follows. So this is our input, right? So it's like okay, so this is the definition of the relative condition number when A is our input and x is our output. Okay, so in this case, this is a dA that I wrote, and so given this equation, and then still we view this b as a constant, and then a plus delta a. And also let's think of this x and its perturbation, or the difference, as a result of perturbation of a, because a is considered as input and x is output, and so we have to satisfy this kind of equation. Again, b is still considered as a constant, right? So in this case, if we just distribute this, and then a times x plus delta a x, okay, plus a and delta x plus delta a and delta x. Okay, So it's something, yeah. So what is the delta x, delta A? So in this case, if A is 1, 2, 3, 4, and then we can consider a small perturbation that we add to the this matrix. For example, 0.2 and negative 0.1 and negative 0.3, for example. Okay, so this can be viewed as this delta A, okay, which represents the perturbation of this original matrix A, right? And then due to that, the resulting perturbation that is generated for the X. And so, okay, so in this particular example, the real scenario is like now let's think of this linear system. Okay, and then I generated this example having the solution in mind of, yeah, which is like 2 and 1, right? So without any perturbation of a matrix and fixed B B vector, and then the corresponding output of X will be 2, 1, right? But what if we just used this kind of matrix, which is an inaccurate version or perturbed version of our input matrix, and then what will be the corresponding solution of this x1 and x2, and then what's the difference between that resulting solution and this original solution of 2, 1. So that is corresponding to this delta x, which is still a two-dimensional vector. Okay, so yeah, you guys now understand this equation through this example. Then yeah, it is still B, right? And then if we think of this like pre-perturbed version of A and X, and then it should be able to satisfy this B. So we can cancel this out, and then and then in general, yeah, let's think of the scale of this A and X and delta A and delta X. So it has the scale of like 1, 2, 3, 4, which is the range between 0 and 10, for example. And then like this small perturbation of 0.1, 0.2, and negative 0.1, negative 0.3. So those will have a much small kind of scale. So yeah, let's think of the scale of this the perturbation of A as maybe 10 to the negative 6, for example, and then X is having the scale of 10 to the 0, for example, because it had the solution of 2 and 1, and it's roughly having the range between 0 and 10. Okay, and then let's see, and then this one has the scale of approximate scale of 10 to the 0, and then this one would have maybe 10 to the negative 6, for example. I mean, that's just an approximate or one simple example, hypothetical example. But due to those scales, if we just multiply these two delta parts of an A and X, and then it will have 10 to the negative 6 and 10 to the negative 6. And so compared to those two terms, okay, this guy will have much smaller scales because after multiplying them together, and then it will have much smaller scale. And so yeah, we can just remove or ignore this part in this equation. Okay, so we ignore this because it's it has so small scales, and also before considering the pre-perturbed version, and then AX should be equal to B, and so it is cancelled out, and thus our conclusion is this guy. Multiplication of these two terms, and then the summation between these two, that should equal to 0. Okay, so why do we do yeah, why do we do this kind of manipulation of this equation? We want to be able to obtain this relative condition number, right, of this linear system when viewing it as a function of an input of an x, input of an a, and then output of an y, x. Okay, so we want to obtain this delta x, in terms of the original input of an a, and also its perturbation, and also maybe its original input vector x. Okay, so in this case, we can easily obtain this equation. Okay, we just move this to the right hand side, and then take the multiplying the inverse of matrix A, right, and then we obtain this, right. Okay, so given this equation, we can now derive our condition number in this scenario. So this is the original definition that I just wrote over here, and then this delta x is a product of these three parts, right? And then due to the Cauchy-Schwarz inequality that we utilized in the previous example, we can also represent the norm of the entire product. Okay, the norm of an entire product, which has the upper bound of the product of the norms of each element, like this. Okay, so we have these three elements, and then we just take the norm of each, and then multiplying it, and then they will provide us with some upper bound of the norm of the whole product. Okay, so once we just manipulate it into this form by introducing this inequality, and then now, given this equation, we can just conveniently cancel this out. Okay, and so finally we obtain this. So in this case, if we consider two norm of our matrix or vector, I mean, in the case of matrix norm, we consider this induced norm, and then we understand this is the smallest, the reciprocal of this smallest singular value, and then this one is the maximum singular value or largest singular value, and thus it is still ending up with the relative ratio between the largest and the smallest singular values. Okay, so the conclusion is really the same between this particular example, okay, or the previous example, which was much simpler, like just a simple matrix and the given input vector and their product. Okay? So intuitively in this case, and A and X was our input, and the resulting vector, just denoting it as Y, and then we obtain this output of an Y, and then given these two two different inputs that we have to give to run or perform this function, we consider the relative condition number with respect to this input and this output, right? But now we consider this case for example, y equals x, or this b when considering the linear system, right? So in this case, what is the input? Input is a, and this x, for example, when denoting this part as our x, and then still the scenario is almost the same, except that we just change it between the row of, or the position of x and y in the same equation, right? And then the input is a and x still, but x is over here, okay, and then this is y, right? So given this this function form, we now obtained the condition number when considering the input as this A, or perturbing one part among between the two, which is our A, and then we consider the the resulting or corresponding relative changes to Y, right? So that was what we just did in this particular slide, right? So the derivation was a little bit different, but the conclusion is still the same. The ratio between these two, largest and the singular, smallest to singular values, and so the lessons here, in summary, is that if we have a small gaps between these two numbers, and then it will provide a better condition number, and thus it will have a kind of less potentials in giving like inaccurate solutions. So although I didn't give particular examples, but you can just think of it as like a bad thing when having a large, the large condition number or the large gap between these two. Okay, so that is the notion of this condition number, and then we can think of this condition number for many different types of a function, and also related to this condition number, there is the notion of this stability. But I'm gonna just skip this part. But at a high level, I will just give an brief like a sense of the meaning of this stability. So stability means like, so our machine cannot differentiate between the two numbers if the two numbers differences are like less than maybe 10 to the negative 16, right? So in general, this is called the machine precision, right? And this number is the smallest number that the machine can differentiate, or if the number, the difference between these two numbers are smaller than this, and then our machines cannot differentiate those two different numbers. And where is this number coming from? So this was coming from the floating point operation, or floating point number representation. So let's see. In the case of single precision, we use 24 bits as our significant, right? And in the case of double precision, we use this 53 different digits, or the binary digits, to represent the significant. That is just the following. After this 1 point, or this decimal point, and then all these numbers are used to store. These 53 bits will be used to store all these numbers, right? And so it means that at the 54th digit, okay, to the right of this decimal point, and then the machine cannot differentiate that, right? So that number is like this number is roughly computed as 10 to the negative 16. Okay, and also this, because we are using this floating point number representation, and so this machine precision is defined as a relative number, right? So just to review quickly, the definition of this relative. Okay, so if you remember this slide, and then given this original point of an x, and then we consider it's a norm. If it is a vector, and then we can just extend it to their norm, and then given the magnitude, of this original value, and then the relative ratio between these two. Okay, so if that is becoming like the smaller than this value, and then yeah, we cannot differentiate between these two numbers, right? And so from the computer's perspective, as long as the relative differences between the true value and the approximated value by the computer is smaller than that value, then that situation is considered as just fine. Okay, that is like just kind of reasonable situation that we can tolerate, right? But if during some computations that we go through, whether it is a matrix multiplication or the linear system solving, yeah, or any other, maybe some nonlinear units and so on, and then if we consider it's a true output and then the approximated output that was generated by our inaccurate computations done in our computers, and then if that difference becomes larger than that number, and then that is the situation that we have to kind of worry about. So yeah, those stability, or the notion of this stability, is like throughout the entire computational process that we go through. Okay, if the condition number, if this relative difference is still within that 10 to the negative 16th, I mean, yeah, considering this 64 digit floating point representation, and yeah, if the number difference is like within this range, and then the whole computation is considered as stable. But during our computation, or yeah, after doing some matrix multiplication, and then if the output, yeah, can have this larger errors, then it's with respect to its original value of an output value. Okay, in that case, that computation is considered as like not stable, or yeah, unstable. Okay, so that is the notion of this stability. And also, yeah, this stability, I mean, the computation becomes like unstable for a particular input value, right? So in this case, we saw the example of the example of really large relative condition number, right? So in this case, if this relative condition number becomes large, and then it assumes, or it happens when a specific condition happens, or this specific condition is met, where this x1 and x2 is approximately the same with each other. Okay, so that was just a high-level explanation about this stability. But yeah, due to the time constraint, I will just skip most of the details about this stability. But I mean, just to let me add one more thing. So so there is a kind of two notion of the two kinds of a stability. So the first one is the forward one, and then the other one is backward one. And so the forward one is like the considering the original function of this guy. Okay, so here the question is, if x is perturbed within the machine precision, or within the 10 to the negative 16th, and then the question is whether this perturbation or the error corresponding to this output value is still within the machine precision. So that is our question that we consider when considering this forward stability. But in the case of backward stability, okay, so it is reversed. So we consider first like the machine precision, I mean the smaller differences than the machine precision for the output value, and then what will be the possible amount of the perturbation that we can consider in terms of the input value. Okay, so in that case, we kind of consider this inverse function of this relationship, and so that is corresponding to this backward stability. Okay, and then also this class title is not just a linear algebra, but it is about like a numerical linear algebra, right? So this term called the numerical stuff. Okay, so this term is in the the main topic in this numerical linear algebra is considering all these inaccuracy introduced by the by our computer, mainly due to this floating point operation. Okay, and in practice, this unstable situations just happens, or this unstable situation happens mainly when we divide some number by close to 0. Okay, so we will also see this kind of example of this stability issue when studying the next topic of the LU factorization. But if we just saw this example, okay, so here we see this the absolute value of the difference between x1 and x2 if it is close to 0, and then we will just divide some number by 0, and so the value will just explode because it is divided by close to 0. And so that is the main source of this bad condition number. So so the main idea is like this. So suppose we just divide it by this a small number, okay, and then it will be like 2000, okay, but somehow we represented this number as kind of an inaccurate number, like, so I just mistakenly represented it as this 0.002, and then the division between these two numbers will be 1000. Okay, so the difference between these difference of the result between these two cases will be really exaggerated, right? So even though 10 to the negative 16, I mean the differences in terms of this really small scales of the numbers that we deal with, but even if this small numbers, I mean if this number is involved, especially in the denominator, when having to divide some number by that, and then that will create a really large inaccurate number. Okay, so that was about the conditioning and the stability, and then we will move to the next chapter of LU factorization. Okay. And before starting this new chapter, I mean this is our last class, right? And also exactly in a week, like next Wednesday at 10 a.m. 10:30 a.m. We will have a final exam. And there are many stuffs that I wish I could cover, and if you're interested, there is a lecture videos that I uploaded when I gave the same lecture about 2 years ago. Okay, so that keyword is like I think I listed the link to this to this playlist in the YouTube, but 2016 and the second semester, and numerical kind of linear algebra. And although that is a Korean lecture, I mean the lecture that I gave in Korean, and this lecture will cover the rest of the stuffs that I wanted to cover. So just if you're interested, and then you can look at this lectures later on. Okay, and given the remaining times, I will do my best for today's lecture to cover as much as possible. And so yeah, let's just study this LU factorization. And I think you guys know, yeah, about this LU factorization. So we basically consider, yeah, for example, this square matrix. But I believe this LU factorization can be, yeah, can be defined for the rectangular matrix. But I may be wrong. But yeah, it doesn't really, yeah, it is not that important. But yeah, let's just assume we are given a square matrix, and then given this square matrix of our input, and then this LU factorization is like a iterative process of making this matrix into upper triangular matrix, which we call as a U, okay, matrix U, which denotes the upper triangular matrix. And then in this case, how do we change this matrix A into upper triangular matrix? It is through multiplying some matrix on the left of this original matrix, okay, and then from here to here, yeah, we just introduce the zeros on the first column, except for its diagonal element and the above element, and then we achieve this. We obtain this matrix by multiplying some matrix called L1, and then this is corresponding to the result of an L1A, and then we multiply another matrix L2 to introduce 0 over here. Okay, so through this consecutive multiplication of this L1, L2, and so on the left of this input matrix, and then we end up with this upper triangular matrix. Okay, and so let's see. So overall, this L1 through L3, and the product of this will be the lower triangular matrix. Okay, so these the product of these three matrices are lower triangular matrix, and then once finishing this process, and then we will end up with the upper triangular matrix, and then this whole part will also be the lower triangular matrix, and also in order to move it to the right hand side in the place of this, okay, and that is corresponding to this L, right, where L is the inverse of the product of these matrices that we used to make the matrix A into upper triangular matrix. So this whole part, the inverse of this product of all these matrices, will also be lower triangular matrix. Okay, so yeah, it can also be called as a kind of triangularization. So what that means is, so we are making this matrix A into a triangular, or more exactly, upper triangular matrix, right? So we are triangularize the input matrix, and how do we triangularize this input matrix? We are multiplying the lower triangular matrix, right? So it's like we just use the lower triangular matrix, and it's a multiplication with the input matrix A, and as a result, we can triangularize the original input matrix. So if you remember this kind of notion, like making some matrix into another form using some other matrices. We also considered like Gram-Schmidt's orthogonalization process. So if we consider this A as QR, right, and in this case, we can directly think of this, but we can also think of like considering this orthogonalization, and then Q transpose A is becoming R, right? So in this case, we are making this A, or triangularizing or making this input matrix A into upper triangular matrix R by using some orthogonal matrix, right? So that was like orthogonal kind of triangularization. So this term was also used when studying this Gram-Schmidt, and also the house order transformation. Okay. Okay, so let's think of how we make this triangularization or upper triangularization of the original input matrix. And so here, okay, let me change it as maybe 3. Okay, so in this case, we want to obtain this matrix, the first matrix L1, and then how can we introduce zeros in this place? So in this case, we just multiply this matrix L on the left, and this is having this form. So it has, it starts with the identity matrix over here, and then we just carefully determine those 3 values, and all the other values will be just the same as identity matrix. Okay, so actually this LU decomposition or LU factorization is part of the undergrad like linear algebra curriculum. So I believe you guys are you guys are familiar with how we obtain this L matrix. And so how do you obtain this value? So in this value, so we can view the multiplication with this matrix and this input matrix as the row sum, the row combination. So if we multiply this on the left of this matrix, and then each row is providing the linear combination coefficient that will be associated with each row of our matrix over here. So we have 4 rows, and then if we consider this first set 1 0 0 0, and then it is corresponding to like 1 0 0 0, and so it is just choosing the first row. Okay, so that will form our first row in our matrix. And then what about the second row? Okay, what about the second row? In the second row, we multiply the this second row by 1, and then 0 0, and then we are multiplying this value. So let's call it as A, B, C, and then we have the multiplier as A, right? And then that will form our second row in the resulting matrix, right? And then let's think of the way of making this value as 0, and then this value was originally 5, and then 5 times 1, and then 3 times A should be 0, right? And so A is what? Like this value, negative 5 over 3, right? So when plugging this value into this place, and then if we just do the linear combination of these 2 rows, and then we can create this as 0. And then similarly, if we consider this B as another variable to determine, and then in that case, this guy is B, and this guy is 0, and 1 and 0, right? And so we are picking up this by just multiplying 1, and then we have to multiply this 3 times B. That should be equal to 3, right? And so this B is negative 3, right? So this is how we obtain this first step of a lower triangular matrix of L1, right? So in general, yeah, if we generalize this process and then yeah, let's think of this kind of matrix as our input. Okay, and then the corresponding L1 should be like 1 1 1 1, and then in this place it is negative a b over a, and the negative a c over a, negative d over a. Okay, so using this row linear combination of the rows, and then this one is our L, right? And then when multiplying L1 over here, and then the resulting matrix will be A and 0 0 0, and we have some value like this, right? And then this is, okay, this is the matrix that we see on the, in this place. And then why do we write this part as like a bold X mark, okay, compared to this plain font X mark? So this is because those values are still assumed to be like a non-zero, potentially non-zero, but these values are certainly different from the original value, 6, 7, 8, and 10, 11, 12, and so on, because this guy is the result of the linear combination of this row and also this row when multiplying this row by this number, right? And so we will generally obtain a new non-zero values, right? Okay, so this is a how we compute or how we obtain the first L1, and then how do you obtain L2? So in this case, suppose our value is like 5 and maybe 8 and 11, and then similarly L2 is obtained as like 1 1 1 1 and 0 0 0, and now we just change those two numbers, and this number is negative 5 over 8, and this number is negative 8 over 5 and negative 11 over 5. Okay, so once we obtain this L's like L1, L2, and so on in this manner, and then at the end we will obtain upper triangular matrix, and then the product of this L's will be just a lower triangular matrix. But here there is a kind of some interesting properties in this LU factorization. So let's think of the first L as so this was L1, and then the next L2 was see, we are using these numbers. Okay, so given these two matrices, how can we obtain or compute the matrix multiplication? I mean, we can just multiply these two matrices, right, by just doing this inner product and then this inner product and so on, right? And this will be like a standard way of multiplying these two matrices. But if we obtain this L1 and L2 in this form, and then our resulting matrix of this product of these two will be just filling up this column into here. So it was 8, right? 8. I mean, the actual numbers are not that important, but the point is, we are just copying it through this part, and then we also copy this part into this part. So here the main point is that we don't actually need to compute the actual matrix multiplication between these two to obtain the product of these L2 and L1. Okay, so in this case, yeah, let's try to understand and prove why we don't need to multiply. I mean, why we don't need to perform the actual multiplication between these two matrices. Okay, so yeah, let's just represent each of this lower triangular matrix L, just like this guy or this guy, yeah, into another form like this. Okay, so here let's just, yeah, for example, the first matrix of an L1 can be represented as this form. So we just start with identity matrix I, and okay, some form like this. Okay, so in this case, I is 4 by 4 identity matrix, and this guy is also 4 by 4 matrix that is subtracted from the identity matrix, and here L1 is defined as just a single column vector, and that column vector is like 0. Yeah, so yeah, we just copy this part into here. Okay, so so I shouldn't have used this complex number, but okay, so yeah, we consider this matrix, this column vector, and this E1 is just a standard unit vector. Like if it is a E1, and then it's like a 1 0 0 0, and if it is a E2, and then it's like 0 1 0 0. Okay, so that is a standard unit vector that we are familiar with, and then we consider it's a transpose version, and then it is like 1 0 0 0. Okay, so in this case, the resulting matrix is putting or placing this column vector in the place of the first column of the entire matrix, and then the second column and the third and the fourth will have just a 0 column, right? So this outer product multiplied with this unit vector is like putting this column in the first column, right? And if we consider the unit vector of an E2, and then we will put this column vector in the second column, right? Okay, and then oh yeah, we have a negative sign over here, and so let's just negate all these values because we have negative or the minus sign over here. Okay, so we can now represent L1 in this form, and then let's also represent L2 in this form, and then this L2 is like identity matrix, and L2 and E2 and transpose, and you can now understand what the L2 is. L2 is like 0 0, and we just bring this column into this part, right? And so okay, and E2 is 0, 1, 0, 0, right? Oh yeah, we need a plus sign over here. Okay, so this is our L2, and then let's just consider the product between these two matrices of one L1 and L2 in this form. Okay, and then okay, so let's just evaluate this. Okay, so this is just a distribution of this product, right? Okay, so here yeah, let's focus on this part. Okay, and considering its shape of the matrix, as we saw in the previous slide, and this guy is like L2 and E2, right? And this is an L2 and E2 transpose, and also this is an L1 and E2 E1 transpose, right? So the product of these two outer product, and in this case we can multiply these two together, right? I mean, yeah, we can multiply these two inner product first, and then once obtaining the single scalar, and then we can move it on the left part of this whole product, right? And then now yeah, this outer product, I mean the product of these two outer product can be reformulated as the inner product first in the middle, and then bring it outside, and then we can just compute the second inner product between these two numbers, right? Or two vectors. Okay, so at a high level we can kind of manipulate this entire product, and then when computing this inner product in the middle, so this E2, okay, E2 is 0, 1, 0, 0, having only the non-zero element in the second element, I mean in the second position. And then what about this L1? Okay, what about this L1? What was our L1? So L1 was this guy, right? This guy. And then the first value of our L1 will always be 0, because this guy, yeah, I mean, when forming this L1, we just needed to obtain this part, which is a lower triangular part, and along the diagonal, we just set, or we just have just a 1, which is just coming from this identity matrix, right? And so this L1 will always have 0 over here, right? And those non-zero values to create or to introduce the to introduce 0 in this part, right? Like in general, as I mentioned, like if we have this matrix as an input, and then this is our L1, and what is this small L1 as our column vector, and that column vector is 0, and this part being placed over here, right? And so we can always guarantee that the first element will be always 0. Okay, so Okay, so yeah, this guy doesn't create the 0. Okay, so so the point is, between these two vectors, if the non-zero elements are not overlapping, and then it will always lead us to the value of 0. Okay, so that is the point. So in this particular case, it doesn't give us the 0, but let's just consider this value as some value, and then move it to the left, and then consider the product of, the inner product between L2 and the E1 transpose, right? So in the case of L2, as we saw in the previous case, at least, yeah, if it is an L2, and then at least we will see two zeros as a leading, or the first elements, and some non-zero values over here, right? Because what was L2? So L2 is corresponding to this part, right? That is filled in this initially 0 vector. Okay, so in the case of an L2, up to the second position or second element, we can always guarantee that they are always 0 and non-zero values after them, right? And then here, let's consider the inner product is the inner product with the E1, and then E1 will have this first element as 1, and then another element as all zeros, right? And so here, if we consider the inner product, okay, and then the non-zero values on the right matrix will have only 1 in the first place or first position, and then if we consider L2, and then it will have like a 2 0 elements, and so it will have a 0 as a result of the product, and the rest of them from this unit standard matrix, unit standard vector, and then it will have zeros, and so this whole part of L2 L2 I think I made some mistake, because we are considering the outer product in this case, right? So so sorry about this. So in the middle of this computation between these two, and then it will be inner product, but once moving it to the left, and then still the product of these two vectors will be outer product. So I made a mistake over here, and so let me change the story a little bit over here. So when just considering the multiplication between these two, and then we cannot make this part as 0, but the first step that we need to do before doing this is this guy. Okay, so this is like L2 and L1, right? But when making this L2 and L1 and times A as our matrix U, okay, and then we obtain this LU factorization in this manner, right? And then in this case, this whole part of the inverse of this product, okay, so that can be represented as this one, right? The product of inverse in a reversed order. And so let me just consider first the inverse of each of our matrix L. Okay, so again, the L is like the one of these two matrices, right? So in this case, yeah, we can now represent L in this form, and then let's just consider L1 first, and then L1 is again I minus L1 and the E1 transpose, and then I want to claim that its inverse matrix will be I plus L1 L1 E1 transpose, but we just change it, the plus negative, the minus sign to the positive or the plus sign over here. Okay, so let's prove this in this simple derivation of just product of these two matrices, and then if we obtain the identity matrix, and then this is a square matrix, and then we found some matrix when multiplied with the original matrix, it is generating the identity matrix, and then we can conclude that this guy is the inverse of the original matrix, right? Okay, so in this case we have we have this kind of result, right? So we consider this term, right, that results in this identity matrix, and then this guy and this guy, and then they have the same terms, but opposite signs, and so they will cancel out with each other, and then the last term will correspond to this guy, right? So it's just like x plus y and the x minus y is the same as x squared and minus y squared. Okay, so if this part is 0, and then we can just end up with the conclusion of the result being the identity matrix. Okay, let's then prove this guy will result in the 0 matrix, and then we will apply the same trick. So we have L1 and E1, right? 1 0 0 0 and 0 and some values, right? So this was L1 and the E1 transpose, and okay, so we have another L1, which is the same column vector that we used over here. Okay, then 1 0 0 0. Okay, and then we now compute the inner product in the middle, and then due to this non-overlapping non-zero. Okay, so here we see only one non-zero in the first place or the first position, and then this value will be guaranteed to be 0, and so we're multiplying them together, and then it will produce 0, and then the rest of them will have 0 for this standard unit vector, and then we're multiplying them with another non-zero sets of these values, and then it will create 0, right? So we now easily proved this guy, or this guy is 0, and thus the product of these two will be this identity matrix. Okay, so we proved the inverse of this matrix is represented as this, right? And so intuitively, okay, so if we have this matrix as an input, okay, and the inverse matrix of this will have almost the same form, but we just have positive sign over here, and then it will be the inverse matrix of this original matrix. Okay, so we now represent yeah, we can now represent this L1 inverse over here, and then it is just nothing but I plus L1 and E1 transpose. And then what about the L2 inverse? It will also be the same, right? L2 and E2 transpose. Okay, and then yeah, now I want to prove this guy. Okay, I want to prove the product of this is equal to just this one, which is like L1 E1 transpose, L2 E2 transpose, and then this whole part is 0, right? So yeah, I want to prove that part. Okay, so yeah, we also use the same trick over here. So yeah, my kind of mistake in the previous case was I tried to consider the product of this and what's the difference between this case and this case. So we basically changed the order between these two matrices, and also made the sign of it as plus, right? Because this, when changing the sign of this, and then yeah, it will just make them as a inverse of each matrix, and then yeah, we will just reverse the order. Okay, so in this case, yeah, let's just simply prove this. So we have 0 and some non-zero, and 1 and 0, 0, 0. Okay, and then L2 is, yeah, at least the two entries will be 0 and then non-zero over here, and 0, 1, 0, 0, right? And so E1 will have the non-zero in the first element, right? But L2 will have just the two non-zero elements in the first two elements, okay, in the first two position, and then start with the non-zero after that, right? And so when considering the inner product between these two, and then it will produce just a 0 matrix. Okay, so we proved this part. Okay, this part as 0, and so the product of these two will be represented in this form, right? So what's the implication of it, or what kind of conclusion can we obtain over here? Okay, so in this case, this guy and this guy is the product, okay, product between these two matrices. But so this was original L1 and L2, but when moving it to the right hand side, right, and then we change these two, and we change the sign over here in this form, right? And then yeah, we just switch the order of this product between these two matrices, and then the resulting matrix of these two matrix product, okay, will be represented in this form, right? So in this case, the way of understanding this matrix or this matrix was like, yeah, so starting with this identity matrix, and then we fill up the first column of this lower triangular part, right? And then what about this? And then it was filling up the second column of the lower triangular part, right? And then when adding this identity matrix with these two, like this outer product and also this outer product, right? And then it is just simply like putting this into here, okay? So that way we can completely avoid any kind of multiplication that should happen normally in the matrix multiplication, but we just fill out these non-zero numbers into the corresponding positions, and that will give us the whole product, okay, whole product of this part, right? So that will give us our L. Okay, So this is the main trick that we use when doing the LU decomposition. Okay. Yeah, which allows us to avoid this actual matrix multiplication. So yeah, I will skip the details of this pseudocode, and then this LU factorization can be viewed also as this Gaussian elimination process. And then we now think of this pivoting. Okay, so the pivoting. So pivoting means, suppose we obtained this kind of intermediate lower triangular matrix during our computation. Okay, so we had an original matrix, and then we just introduced zeros in the first column. Okay, and then here, yeah, 3, 5, maybe 11, and -2. Okay, and then we will do our matrix multiplication with the L2 on the left to introduce these values as all zeros, right? So that will be the second step, right? But here, let's think of this kind of scenario. Yeah. So in this case, yeah, how do you obtain this L2? So the formula for L2 will be like 1, 1, 1, 1, 1, and what was this element? So this element is -5/3, right? And the second element is also the -11/2, and then the third element is -2/3, right? Okay, so here let's think of this kind of scenario. So what if we obtained this value as just 0, or maybe some number close to 0, for example 0.001. Okay, so which is really small number. So in this case, this one will play a role of this denominator over here, right? And so in this case, it will it will kind of enlarge or increase the original value through the division of this small number, right? So this is the situation that I mentioned in the previous kind of stability issue kind of stuff, right? So if we have a really small value and then dividing it by that, and then if this small value was not precisely represented or accurately represented, and then we may introduce really large number in our matrix L or during the subsequent computation of this LU decomposition, right? So again, as I mentioned, again, like dividing some number by close to 0 or really small number is really, may create a really bad thing. So that is the main lesson today for you guys. Okay, so in this case, we can think of like something called a pivoting. Okay, pivoting. So pivoting means, okay, so yeah, let me be a little bit more flexible when doing this LU factorization. So in this case, we understand like dividing some number by small number is a bad thing. And then how about just dividing those number by like a big number among them? So we have these 4 numbers, and then what is the biggest number? So biggest number is 11, right? And then what if we just use this number as denominator and then introduce 0 over here? Okay, so we can certainly do so, because in this case, what will be the corresponding kind of L matrix over here? So in this case, so we will have 1, 1, 1, 1, 1 over here, right? And then we want to create 0 over here by using this row, right? And then in the case of the second row. Okay, in the second row, in order to create the 0 over here, we will use the linear combination coefficient over here. So in this case, we can have 0, 1, 0, and what is this number? This number is 11 by, 0.001 by 11 and maybe negative, right? And then 0. And then using that as a linear combination coefficient of those rows provided on the matrix on the right, and then yeah, we will have like a 0 and the 1 as a linear combination coefficient, and 0 and like negative 0.001 and divided by 11, right, and 0, right? And then once combining them, and then we can introduce 0 over here, right? Okay, so in this case, if we think of this relation, and then what will be this number, and this number will be minus or negative like 5 over 11 if we had a 5 over here, and then in this case we will have 2 over 11, right? So in this case we can certainly avoid this division by really small number, because we chose this the largest number possible among what we have over here. But in general, we don't do this kind of thing, because in this case, this is no longer be the lower triangular matrix, right? Because we have some non-zero values on the upper diagonal part, right? So we don't do this kind of step, but we do kind of equivalent step by introducing something called a pivoting, or like column shifting, the row shifting. So in this example in particular, we can actually do another operation in the middle of changing, if we identify the biggest element along this elements that we have to introduce zeros to, and if we found this largest one, and then we move it to this element. And how do we do so? We just do the row interchanges. Okay, so in this case, to make this matrix, suppose we multiplied L1 first, okay, and then this is our intermediate result, and then 11 is the biggest one, which is found in the fourth column, not in the second column. Okay, so in this case, we multiply this matrix called the P1, which is called a permutation matrix, which is just doing the row interchanges. And if we want to change this 2 rows of the second and the fourth row, how do we obtain this P1? Okay, in this case, P1 will be like 1, 1, 1, 1, 1, right? And then we just pick up these 2, or choose this second and the fourth rows, and then just to change it into like 1, 1, and 0, 0, right? Right. So basically, we consider this a 2 by 2 matrix, and then initially it was 1, 0, 0, 1, which is just a 2 by 2 diagonal matrix, but we just change between these 2 rows, and thus 0, 1, 1, 0, and that is the resulting matrix that can play a role of like interchanging between these 2 rows, right? So we can, introduce this row interchanges to avoid this undesirable situation of having to divide some number by close to 0. Okay, so in this case, we have L1, and then we do this. This is called a pivoting. Okay, so this is called the pivoting, and then we do this pivoting of changing or bringing the largest possible value into the diagonal element by doing the row shifting, and then we perform another triangularization. With the one more step, and then we identify another largest element in the corresponding column to introduce 0, 2, and then L3 and P3 and so on, and then that will result in the upper triangular matrix. Okay, so I mean, yeah, this is not the end of this LU vectorization with the partial pivoting, and so yeah, in this case, this L and P is all mixed together, like in this kind of order, right? So they take turns. I mean, they appear like in this, L1 and P1 and L2 and P2 and so on. But here, yeah, we want to obtain this kind of thing. So P3, P2, and P1 and matrix A. Okay, and L3, L2, L1, and U. Okay, so in this case, yeah, these L matrices will be slightly different from the original L1 through L3. So that's why I wrote it as a L3 prime, L2 prime, and so on. But yeah, we will study how to change this into this form after the break. Okay, so yeah, let's take a break until 12:05, and then yeah, we will resume after then. 예, 안녕하세요, 대표님. 예. 아, 예.
그 스타가 빛이 돌린 줄 알았어요. 아직 변화 없으세요? 안 되겠죠, 시간이. 근데 사실 이제 그때 말씀드려가지고 약간 좀 이건 너무 야한가 싶어가지고 스타가 빛이라 돌릴까 했는데 도저히 안 되겠더라고. 너무 하기 싫고. 제이슨 파일 있었어요. 다른 걸로 하나? 예전에 그래요? 제이슨 파일 못 본 거지? 그거 있었어요, 제이슨 파일. 거기 일단 제이슨 파일에서 네. 수정하지만 이제 씌워줘야 돼요. 그게 앞으로 있었어요? 네. 좋네요. 근데 그거를 엄청 크게 했는데도 금방 돼가지고. 그럼 전혀 좋은 네. 오늘 밤 11시 50분까지 맞죠? 다른 분들은 다 있대요. 하고 있어. 저만 안 하고 있었어. 다들 두 분은 어떻게 하시네요? 효진님이랑 그래서 네. VA 똑같이 거기에 VA 좀 해가지고 사람들 역시 다 똑같네요 진짜. 그래도 파일은 파일만 파일만 낸다는 거 딱 보자마자 아 이거 안 해야겠다 싶은 거예요. 버려야겠다. 사이클 스포츠 큐. 사이클감도 저희 똑같은 걸로 돌렸었나요? 똑같은 그 랩으로. 유튜브 거기 쩐나기라도 해서 다행이겠다. 끝까지 내가 했으면 진짜 절망적이었을 텐데. 전철 이런 거 어떻게 한 거야? 하나도 모르겠다. 아 선배 이거 되게 거의 안 나왔거든요. 중간고사 이거 거의 안 나오더라. 교수님 화났었잖아요. 그때부터 해서 지금 선배 지금 중간고사 떠나지고 지금 그러니까 지금 교수님 맨날 이거 생략하는 게 있어요. 이거 안 할 거예요. 넘어갔어야 되니까. 과잉고 필요해. 제가 안 나왔을 그때 분명히 이런 거 좀 많았던데 이게 많았을 것 같은데. 무슨 동영상 있어요? 이거 외국 올리세요? 아 진짜요? 근데 몰랐어요. 어디 올라와요? 아 진짜 몰랐어요. 길버트 스트링 다시 걸려서 못 보겠네. 다행히 오늘 되게 좋은 정보 원래 항상 올라왔었어요. 그냥 혼자 있어요. 그때는 그래도 지금은 컨디션 너무 좋아서 처음 보는 컨디션 너무 좋죠. 그걸 또 알고 나니까 너무 잘했다. 이따가 다른 수업 데이터 아날리시스 베이직이나 딥러닝 하늘에서 이렇게 나왔어. 그거 주소 바꾸고 싶다고 나한테 그래서 이승주 선생님한테 물어보고 이승 선생님께 정보 전산자 담당 업무를 맡으신 연락처를
위험해. 안정이 눈썹까지 지금 올라오고 그래가지고 그 눈썹에 애매하게 걸쳐져서 이 눈썹 저 돋보기 되게 파괴를 못했어. 그걸로 바꿨어?
그게 좋은 거 같아. 내 얼굴을 좀 가려줘서 얼굴 가리고
눈썹까지
얼굴 가리고
하나한테 걸 써가지고 이렇게 위에다가 하나 이렇게 하다. 요구이 차가 그거 하니까 가격 나 엄청 많아. 압축을 4번 해야 된다고 했는데 3번 했어. 4번 하고 인형 빠지고 자연스러운 거.
Okay, let's continue. So we are discussing about this partial pivoting. Okay, so the main idea is to maintain as much stability as possible, right? And so, yeah, we just switch or interchange the rows so that, yeah, among those elements that we have to introduce 0, and we always move the largest, the largest value, okay, to the top row, so that we can divide those other numbers by that largest number. Okay, so in that case, as I mentioned, yeah, we will, we can write the entire process in this in this manner. So given the matrix A, okay, so in the first place, we've performed the partial pivoting first to also make or select the largest possible number along the first column. Okay, so that way we first perform this partial pivoting, and then the triangularization, and, and then pivoting through the row interchanges and so on. Okay, so in this case, as I mentioned, this intermingled product between L's and P's, and then we can rewrite it in this form where we move all of these P's to the rightmost part, okay, and then followed by the matrix, the product of this matrix L's on the left. And in this case, we can also move it to the right hand side, and then we finally obtain this PA equals LU, because this entire part is P, right? And then if we think of this P, and then from here, let's suppose we apply this permutation or this row interchanges along this column matrix, column vector. So in this case, we will always, the second column will always involve, and then among those elements, including this, if this is already the largest elements among these 4 elements, and then this partial pivoting or this row interchanges will be just the identity matrix. But if maybe this guy is the largest, or this guy is the largest, and then it will interchange between the second and the fourth, and also second and the fourth, right? So the second column, the second row will always be involved, right? Okay, and then suppose we introduce the 0 over here, and then what will be the next or the subsequent partial pivoting matrix P or permutation matrix P, and then it will always involve the third column, and then if necessary, we will choose fourth and the fifth column to interchange it between the third column, right? So this matrix P's will also have some special characteristics, like so in the case of P1, it will always involve the first row, and then one of the lower rows, right? And then in the case of P2, it will always involve the second row and one of the three to the rest, the third to the rest of our rows, right? So it also has this special characteristics. Okay, so let me show the main trick that we use, or that we change the upper equation into the lower or the bottom, the equation on the bottom. Okay, so the So here the main goal is to move all these p's all the way to the right, and then move all the l's all the way to the left. Okay, so that way we can obtain this the product of l's and the p's, right? Okay, so it is a little bit tricky, so in case of maybe 3 by 3 matrix, okay, 3 by 3 matrix, and then we do the row interchanges first, and then do the upper triangularization, right, by using L1s, given this permitted version of our input matrix. Okay, and then we do second step of permutation, right? So, okay, so let's try to move this P3, yeah, one step to the right. Okay, so in this case, yeah, we utilize one important characteristic of this permutation matrix or row interchanges, which is this guy. So it's like so in this case we will change some of these two of these rows, right, and then we do that row interchanges once again, right? So in this case, suppose this guy was changing the row 3 and 4, and then changing once again the rows of the third and the fourth rows of the given matrix, and then yeah, it will have no effect, and thus it will have the identity matrix, right? Okay, so we can put this identity matrix over here. So L3, P3, and L2, and P3, and P3, and P2, L1, P1, A. Okay, so in this case, let's consider this P3, L2, and P3 as a new matrix that we consider as L2 prime. Okay, so in this case, so we use the first P3 over here, and then P3, P2, and L1, P1, and A, right? Okay, so what is L2? Okay, so L2 is, okay, so in the case of an L1, yeah, we have non-zero values in this column, right? And then in the case of an L2 is 1, 1, 1, 1, and we have some non-zero values over here, and all the other values except for the diagonal will be 0, right? So in this case, what's the meaning of this permutation operation on the left and the right? Okay, so so in the case of in the case of P1, it will interchange the rows of the first one and maybe two or the rest of our second or the rest of our rows, right? And then 네. 이거요? 네. 이게 어떻게 되죠? 이게 L1, L2, 네. 여기 하나 더 있으면 이게 L3죠, 그죠? 여기서 끝나죠, 그죠? 네. 그래서 이제 L3까지 가면 이제 이게 4by 4가 되는 거죠. Okay, so in this case, it's interchanging between the first and second, or like a letter column, letter row. And then in the case of P2, it is like changing second and maybe some letter row, right? And then in the case of L3, it is like interchanging the third column and 4 plus, right? You get the idea, right? So when multiplying this row interchange matrix or permutation matrix on the left, and then it will perform, yeah, of course, row interchanges. But still here, given this L2, and then it will just perform the row interchanges of, let's see, yeah, this third column and the fourth column. So if we have more columns, and then it goes further on the left by multiplying P4 and L4 and so on, and then we may have more kind of possibilities, but yeah, but at least we know that it will change the third column in the case of this P3, right? And then some of the other columns, yeah, found on the bottom part, okay, on the lower part, right? And then what about this P3? Okay, in the case of P3 is also, I mean, P3 if it's multiplied on the right, and then it will now perform the column permutation, right? Because it is multiplied on the right, right? So in this case, if it changes the third column and maybe the fifth column, the third row and the fifth row, and then multiplying this matrix on the right, and then it will also change this third and fifth column, right? So does it make sense? So when multiplying P3 on the left and also on the right, it will just, yeah, it will just change the order or the positions of only like 4 elements. Because, yeah, if it was changing third and the fifth row, and then like this guy, okay, and we have one over here, and all zeros. Okay, then okay, so we have some matrix like this, right? And then let's change these two rows, and then x, yeah, and 0 0 0, and then, yeah, let's just bring this column first, and 0x and 0 0 1 and all 0, and then the third column is 0 x 1 and all 0. Okay, so that is the result of this this interchange, right? And then let's also change the third and the fifth column. Okay, so in this case, we will change this column and this column, right? So in this case, yeah, we will change this guy the interchanges between these two columns, right? And so originally this guy was 0, 1 and 1, 0 as a result of this row interchange, because this 3, 3 was 1 and 5, 5 was 1, right? And then 3, 5 was 0 and 5, 3 was 0. And then this is the result of the row interchanges. And then if we do column interchanges between the third and the fifth column, and then it will just get back to just 1, 0 and 0, 1, which is just reconstructing or recovering the identity matrix. Okay, so here the point is, even if we multiplied the column permutation or column interchanges on the right, okay, that will only involve those columns corresponding to identity matrix. But yeah, what was the different part from the identity matrix? So that was like this part that we set by this through this the formation of the lower triangular matrix of an L, right? But those values will be placed on the second column, right? So it is a second column corresponding to L2, but when doing the permutation using P3 for the row interchanges and the column interchanges, and then it will change the third and one of the latter rows and also their columns, right? So in that case, when doing the row interchanges, these two values will change, right? But when doing the column permutation, and then the column permutation will just change those, like 1, 0, 0, 1, kind of this structure was 0, 1, 1, 0, and then it will just convert back to 1, 0, 0, 1, right? Okay, so what is the result? So when applying this row permutation on the column permutation, it is just the same as just changing those two values, okay, in this corresponding column that we have a kind of a non-zero element in. Okay, so in that sense, even if we consider this P3, L2, and P3, this one will still maintain the original lower triangular structure where we have the matrix of this identity matrix, and then if it is L2, then we have some non-zero ones, and then it is just not just having the only effect of changing those two elements, okay, and then all the other structures will be preserved, and so we can view it as our new L. Okay, so that way this P3, L2, and P3 can be written as L2 prime. Okay, but still this L2 prime will have the structure of this form, right? So in this sense, it can also be used. It can also be written as I minus like L2 and E2 transpose, right? So the rest of the process will still remain the same. Any questions so far? Okay, so why do we do this process? So we wanted to move our p's to the right, right? So here, we initially started from here, and then we introduced P3 squared or P3 times P3, which is still an identity matrix, and then L3, and then we now think of this part, right? Think of this part, and P3 and L2 and P3, and that is considered as the new L2 prime, right? And then this L2 prime will include this P3, right? So this P3 is kind of gone, right? But instead, we introduced or we created another P3 over here, right? And so this part is new L2 prime and L3 and L2 prime and P3 P2 and L1 and P1. Okay, so we kind of created an effect of pushing or moving P3 like to the left of L2. Okay, from this position or from the right position of L2, we moved it or pushed it to the right of L2, right? Any questions so far? Okay, so from here, we do one step further. So we now have L3 and P3, L2 and P3 and P3, P2 and L1 and P1. Okay, and then now we want to push this guy to the right place of this L1, right? So in that case, we will have L3 and L2 prime and L1. Okay, so that way we have a product of all L's, right? And then the product of all P's, right? And then that way we obtain this whole sequence of or whole product of permutation times A is equal to like the like this part and the inverse, right? Its inverse will be placed over here, and then we have an LU. Okay. Okay, so this is like a big picture that of our goal. Okay, but let me also reach this conclusion. Let me just erase it. Okay, and then here, we want to move it to the left side of an L1, and so we also do almost the same trick. So here the trick is, so just like we have this L3, L2, and then we move it to over here by just introducing P2 and so P3 and P2. Okay, so in this case, so let's also think of like P3, P2 and their product of the same matrix, and then this one will also be identity because sorry, so here I need to change 2 and 3. Okay, so in this case, what about this P3 times P3? So that will create our identity, and also P2 times P2 will also result in the identity matrix, right? Because we interchange two particular rows twice, and thus it will just end up with the original or the same matrix. Okay, so we can understand this product will also be identity matrix. So we just introduce this whole matrix in this place. Okay, and then now it will be changed into L3 and P3, L2, P3, which is our L prime, right? And then P3, P2 and L1 and P2 and P3. So that is corresponding to like this part is this part, right? Okay, and then we have P3, P2, P1 and the original matrix A. Okay, and then this part is still viewed as another lower triangular matrix L1, as an L1 prime, and that matrix will still have the same structure where we have the diagonal, all ones along the diagonal, and only the lower part of the first column will be non-zero, right? So let's also think of why this structure is still maintained. Okay, so in this case, this L1 is just the matrix. Okay, just the matrix, like maybe this kind of matrix where we just first permute like some column, some rows between the first row and one of the latter row of the given matrix A, right? And then we will just do the normal lower triangular matrix multiplication to introduce all zeros along here, right? Okay, so this is how we obtain L1, but let's modify this L1 by just permuting or applying the row permutation of P2 and the column permutation of P2 and P3 and so on. So in this case, the scenario is still the same. So L1 is, let's use this guy. So we have some non-zero on the lower part of the first column, and then what is the P2? So P2 is like the interchanging the second column and maybe one of the lower column. So maybe second one and the fifth one. Okay, so suppose this guy was the largest one. Okay, so that's why we change it between the second and the fifth row. Okay, so in that case, we do the row interchanges and the column interchanges. Okay, and so it has the effect of changing between these two numbers. Okay, and then even if we apply this column interchanges between the second and the fifth column, okay, so it will just have an effect like this guy. Okay, and then we also do another step of row interchanges and the column interchanges, and in this case, given this matrix L, so we just change between these two, and then if this P3 was changing like a third column and maybe fourth column, and then we also change between these two, and then even if we apply this column permutation, it doesn't have any effect, right? It will just recover the original identity matrix, right? Okay, so this guy will still have like this lower triangular kind of matrix kind of shape, or this kind of forms, and also and so intuitively we can kind of understand that during our LU factorization with the partial pivoting, we just our actual computation, our actual computation is obtained as obtained following this order, right? So we first perform the partial pivoting and then forming this L1s, and then do another second step of a partial pivoting and so on, right? And then how do we obtain this L2 prime or L1 prime and so on, right? So again, in this process, so when obtaining this as U, as a final upper triangular matrix, and then it will be like L3 and L2 prime, L1 prime, and A, and P and A is equal to U, and P is nothing but P3, P2, P1. Right? And so, in the case of obtaining the LU factorization, we will have this PA, and then U times L1 prime inverse, L2 prime inverse, and L1 and U. Oh, L1, 2, 3 prime, Okay, so in the case of an L3, it doesn't have any kind of any of other additional permutation. So L3 will be the same as an original. L3 prime is the same as L3. So we can obtain this, right? So this is the result of the LU factorization when considering this partial pivoting to avoid any kind of numerical stabilities. And then the result is like this. So by looking at this form, so what is PA? Okay, what is the PA? So let's imagine like you performed the actual computation of this actual algorithm following this procedure of sequentially obtaining P1 and L1 and P2 and L2 and so on. Okay, so that is the actual algorithm. And then what will be our output? I mean the final output in this form. Okay, in this form. In this form, we have an A. And then what is P? So in this case, it's P3, P2, P1, right? So in this case, what was P1? So P1 was row interchanges that was identified. During the process of finding out like the biggest element in the first column, right? So if it had the largest element in the fifth column, and then P1 would correspond to like the changing the rows between the first and the fifth row, right? And then what about the P2? And then once introducing zeros, and then we look at this part, and then suppose we identify this guy as the largest one, and then we just interchange between second and the fourth, right? So this is our P2, right? And then let's imagine like a sequential application or sequential permutation. I mean just permutation only applied to the matrix A, right? So in this case, so we are given the matrix A originally, and then we just change the first was the so we just the first interchange between the first and the fifth, okay, and then using the same input matrix, we just change the second and the fourth, okay, and then let's imagine like a P3 was like this guy, okay, and then we will just follow this kind of process of like given this input matrix, we interchange between these two rows and the second and the fourth row, and then the third and the fifth row once again. We just apply this sequence of this row interchanges to the original matrix. Okay, so that is our new input matrix A. That will be the input to factorize. For the factorization of this LU product. Okay, so in that case, U will be the final result after kind of this process of our actual algorithm, right? But how about this else? Okay, how about this else? Okay, so in this case, we know how to obtain this L by just filling out. Let's see, where is it? Once we obtained these sequence of an L's, and then we know how to aggregate or how to obtain the final L, right? So given these L's, and then we just change the signs of these non-zero numbers, and then we just fill out those numbers in the corresponding lower triangular part, right? So this is how we obtain our final matrix L, right? But here these row permutations are involved, right? So so just like kind of this example where we originally had a 0.001 and 5, 11, and -2, although it is a little bit difficult to see. But let's imagine we do the partial pivoting of moving this 11 to the top, right? So we change it between these two rows, and then the resulting L matrix will be like, yeah, so this guy is 11 and this guy is 0.001, right? And so it is like so this is all zeros, and then yeah, we have to fill up this part, right? And so this part is -11/4, and this guy is -11/0.001, and this guy is 2/11, right? 2/11. So once obtaining this L in the middle of like this permutation and the lower triangular and the permutation and the lower triangular, right? So this is certainly like a permuted version, right? And so this is the corresponding L, right? And then we want to obtain L prime from this L, right? And then how to obtain L prime from this L is just following, okay? So given this L, okay, and then we just apply our L's. So if this is an L2, what should we apply to this L2 in order to obtain this L2 prime? Okay, and then it is just a row pivoting, the row permutation, okay, onto our L. Okay, so where is this P3 coming from? P3 coming from. So P3 is the next step of a permutation after we applied L2, right? So once applying this L2, and then suppose our intermediate lower upper triangular matrix is like, yeah, all the upper triangular matrix, and then because it's an L2 and one, and then we introduce the 0 over here, and then we now have to take care of this kind of column in our intermediate like upper triangular matrix, right? And then we will just do the partial pivoting or row interchanges between the third row and also maybe some of the maybe fifth row, right? So in this case, yeah, this permutation is done after applying L2, right? So this is the P3, right? But we apply this P3, okay? We apply this P3 onto this L2, which means we just interchange between these two values, okay? So this is our L prime, okay? So this is our L2 prime that is obtained from L2, okay? And then how about obtaining this L1 prime from L1? So in this process, so we can understand like obtaining this L2 prime from L2 is by applying like the kind of future or the subsequent permutation that we apply, like a P3 and P4 and so on. And so in this case, of obtaining L1 prime from L1, Okay, L1 is like the first L matrix that is applied to the permitted version of the original matrix, right? So A and P1, and then given this matrix of this permitted version, and then we apply L1, right? And so once obtaining L1, and then we will obtain P2 and L2 and P3 and so on. But during the process of moving all these to the power of this L1, right? And so given this L1, right? So 1, 1, 1, 1, and then from here, and then we just interchange by applying P2 and P3 and all the rest of our P's or the row permutations to our L1, right? So this is our final L1 prime. Any questions? Okay. So once obtaining this L1 prime, L2 prime, and so on by just applying those corresponding row permutations, okay, and then we have no problem of obtaining the final L's by just filling up all these non-zero elements in the lower triangular part, right? And then our U is the upper triangular one that we finally obtained through this process of P's applying P's and L's. Okay, so that way we obtain this PA and L and U. Okay, so this is the the complete or entire story of this LU factorization with the partial pivoting. Any questions so far? Okay, and then what's the use or where do we utilize this LU factorization? So the main application of this LU factorization is through it's basically mainly used for solving the linear systems. So we have this linear system of AX equals B, and then in this case, if we obtain the non-pivoted LU factorization without any pivoting, and then we will obtain LU x equals B, right? In this case, we have L and U and the vector x, which is our unknown, and B. So in this case, so we first compute Ly equals solve for this Ly equals B, and then this y can be obtained through the fourth substitution, right? So the first one was like our L matrix is all ones, right? And then B was like 1, 2, 3, 4, right? And then maybe 2, 3, 4, 5, 6, and so on. And then we know the first element of y is 1 because we have 1 times the first variable of y will be 1, right? And then what about the second one? We just plug this in, right? And so in the case of like 2y1 and y2 should be equal to 2, but we already know y1 is equal to 1, and so y2 can be obtained as 0 quite easily in this process, right? So this is a fourth substitution, right? And then once obtaining y, and then we obtain this ux. Okay, so we bring this part into this form. U times x is equal to y, which we obtained over here. And then u is like non-zero elements, having the non-zero elements on the upper triangular parts, and then we do the same thing in a reverse order, right? So we first solve the last equation, which involves only one variable. Okay. So this is how we utilize this LU factorization for solving the linear system. But how about the partial pivoted version, like the LU factorization with the partial pivoting? So in this case, we first obtain this guy as PAX is equal to PB. Okay, so the whole process is like this. So given this matrix A, and then we obtain the form of LU factorization with the partial pivoting like this. Okay, and once obtaining that, and then by plugging this guy into here, and then yeah, we can just first multiply the P onto this original linear system to obtain this PAX equals PB, and then it is now changed into LU x is equal to like B prime, which is or B, where B prime is the same as PB, right? Okay, so in the previous slide, we considered how we discussed how to apply this permitted version of A, right? So in this case, it's like P3, P2, P1, and A. So it's just a sequential application of this row permutation of matrix A, right? So we just interchange those rows. Yeah, that was identified through this process of this actual algorithm, right? To identify the maximum element and moving it to the top. And then we just collect those permutation matrices, and then we just apply it to the matrix L in this sequence or this order. We do the same thing when we just obtain this P times B, because it is like a P3, P2, and P1 times the vector B, right? So if P1 was like the first one and maybe fifth one, and then given the matrix B, we just change the first one and the fifth one, and in the case of second one, and it is changing second and the fourth, and then we also change the B, right? So we have no problem of permuting or interchanging the rows in the vector in the column vector B, and also intuitively this kind of process is nothing but changing the order of equations. So for example, yeah, if we have 2x1 plus 3x2 is equal to -1, and then the x1 minus x2 is 5, and then we can change. Yeah, we can write it as like x1, x2, and -1 and 5. And we can write in this form, right? But originally we can just change the order of these two equations, and thus it means that we are now having like 1, so 1 and -1, 2, 3, and x1, x2, and 5 and 1, right? So we interchange the rows of an A, and then we also correspondingly interchange the rows or the elements in the vector B, right? Okay, so it will have no effect, so it will still give the exact same solution, right? Okay, then once forming this permuted version of our, or the order switched version of our linear system, and then that guy is now rewritten as a LU times x is equal to P prime, and then we follow the exact same process of like this kind of two-step approach of first obtaining this y by just doing the fourth substitution, and then once obtaining y, and then we do the back substitution to finally solve for this solution of this vector x. Okay, so in this process, yeah, why did we need to apply this the row pivoting in this particular case? I mean, why did we need to have this row pivoting or this row permutation in the process of obtaining this LU? Okay, so again, the point is to maintain the numerical stability. So if we don't use the partial pivoting in the process of obtaining L and U, so given this A, so we first have to obtain L and U, right? So we assume that A is equal to L times U. But if we don't use this kind of pivoting ideas, and then yeah, I mean in the case of pivoting, and then we can obtain this PA equals LU. But if we don't use any pivoting at all, and then given this output, okay, and then back to this example where we have, where was it? Yeah, like the problem of dividing some number by really close to zero number, which can exaggerate or enlarge the small error into really big error. Okay, so that will be reflected to the resulting matrix of an L and U, right? So that will create those inaccurate computations of the result of an L and U, and so so in that case, we may have the result that is not the same at all as the original matrix A. Okay, so once you compute just the actual product of these two matrices, and then we can just compute their Frobenius norm between the original matrix A and L times U, and then this error should be really small in general, but this error can be really this error can be really large, if we don't use any kind of partial pivoting. Okay, so in that case, A is no longer be the same as L and U, and thus originally we have to solve for this equation, but changing this equation into this form is based on the assumption that A should be exactly the same as LU, right? But during the process of obtaining this L and U, if we introduce a really large error, which is no longer making them to be the same as each other, and in that case, the solution from here and the solution from here may be really, really different, right? So so in that case, we are just ending up wrong or inaccurate solution for the original equation. So that is the main kind of intuition, or the story about the rationale behind why we need this partial pivoting. Any questions so far? And then in this case, I kept saying this method as like a partial pivoting. So partial pivoting, I mean, we call it partial pivoting because we only do the pivoting partially. But what about, I mean, is there any other kind of scenario where we consider like a full or complete pivoting? So we can also consider something called a complete pivoting. So complete pivoting is, the scenario is like the following. So we know, in the first step, we know that, I mean, we want to select the maximum possible value within the first column, right? And in the next step, we want to select the maximum possible number within that second column in the lower triangular part, right? But what if our matrix is like O zero value along the first column, and then maybe 10, 5, and 13, and negative 12, and then so on. Okay. So in this case, if we only consider the particular column, okay, and then selecting the maximum possible value, and then it may not be our best that we can do. And then here the scenario is like, okay, what if we just expand our scope to find the maximum possible value from into this entire matrix. So in this entire matrix, maybe 1, 2, 3, 4, maybe -1 and -2 and -3, -4. So in this case, what would be the maximum possible value that we can select among the, in the entire matrix? That will correspond to this kind of value, right? So, so in general, we would have to select the maximum possible values as this guy, which is still really small value, right? And so it may introduce, this kind of issue of dividing by really small number, which may introduce the error, really large error. So in this case, how about just changing or placing this largest possible value in our matrix onto the top left position. So this is the main kind of process in the complete pivoting. And then how do we achieve or perform this process? So in the case of partial pivoting, when just considering kind of row interchanges, okay, and then we can also in order to perform this process, we can also consider the column interchanges as well. So in order to move this guy to the top left, we can first do the row pivoting or row permutation between the first and the fourth column, fourth row, and then also in terms of the column permutation, we can change the second column with the first column, right? And then what will be the corresponding permutation matrix that we apply to this original matrix A? So in the case of the row permutation that is applied on the left, okay, and then let's represent it as P. So in general, we will apply P1. So P1, you guys know how to obtain this P1. So we want to change first and the fifth row, and so we just select those 4 elements and then move it in this form, right? So this is the permutation matrix. The row permutation matrix or row interchange matrix. And then how about like a column permutation or column interchange, where we have to change the first and the second column. In this case, it is the same thing, right? So we just select those 2 elements, and then we just make it in this form. Okay, so the process is exactly the same, but the main difference is whether we apply that permutation matrix on the left or on the right. So if it is applied on the left, and then it performs the row permutation, and if it is applied on the right, and then it will just perform the column permutation. Okay, and then once we moving this guy into this position, and then what will be the resulting permutation? And then it is like we just change between these 2 rows, right? And then the changing these 2 columns, right? And then we will obtain the new permuted version of the matrix. But here we achieve the goal of moving the largest possible elements to the top left, right? So that will work as our denominator, right? So divisor. So we chose the maximum possible one. Okay, and then we apply the L1, right? And then we will introduce. So here it will be -20, right? and then we introduced all zeros, and then some matrix like this. Okay, and then it's time to introduce zeros on this part, right? And then how do we apply this complete pivoting in this particular case? Okay, so if we extend, or if we generalize this scenario, then the matrix that we consider is this guy. Okay, this submatrix. Okay, once obtaining this intermediate upper triangular matrix, and then looking at this submatrix when excluding those two rows and columns, right? And then this is the submatrix of our interest, right? And then here the scenario will be the same. What if we just see all the row values, or really small values over here, but suppose we found the largest possible value over here, right? And then we want to move it to this position, to the top left, right? So in this case, we can do the row interchanges between the second, because this is originally the second one, second and the third row, and then the second and the fourth column to move the largest possible value into this top left position. Okay. So in this case, we can apply this P2, right, onto this whole matrix, and maybe Q2, right? And then we will finally, maybe we can do one step further, P3 and L3, and maybe Q3, and we obtain U, right? Okay, so in this intermingled representation of L3, P3, L2, P2, and so on. We know how to move all the L's to the left and all the P's to the right. Okay, so in that case, we can just represent it in this form. So all L1 primes on the left, and all the row permutations on the left of the matrix A, and now you have all the column permutation on the right of the matrix A, right? So this is the form of the LU factorization of the column pivoting, right? So all the L's and the P's and A and all the Q's, which are column pivoting. Okay. So in general, if we just think of this whole product of the column pivoting or the column permutation as Q, and then PAQ is equal to LU, where we just take the inverse of it, and then canceling it out or moving it to this part, right? Okay, so this is the LU factorization version with the complete pivoting. Okay, so let's utilize this guy to to solve our linear system. So PAQ is equal to LU. This is the result of the LU factorization with the complete pivoting, and then we are initially given this AX equals B as our linear system. Okay, and then now we want to obtain this PAQ, right? Okay, so in this case, we just change it to PAX is equal to B. Okay, and then how can we put this matrix Q, which is the product of whole column permutations, on the right of the matrix A? So it is a little bit, it has a little bit issue, or it is non-trivial, because we cannot really multiply Q on the right of the matrix A, because we have an X over here. So if we want to multiply Q, for example, it should be something like this, which doesn't even, which is not even defined, because it is a vector and vector, and these two are column vectors, and the Q is matrix. So it is not even defined, right? So we cannot write it in this form, right? So in this case, we apply another similar trick that we frequently used when moving all the L's to the right. So in that case, PA, and so this Q, if Q is Q1, Q2, and Q3, right, which is the column pivoting or column permutation that we had to apply to move the maximum elements to the top left. Okay, and then in this case, we also change this equation in this form, because this whole part will be identity matrix. Because Q3 times Q3 will be identity, because it's a column permutation between maybe third row, third column, and maybe fifth column, and then maybe Q2 will be the column permutation of the second column, and maybe fourth column, and so on, right? And so once applying each column permutation twice, and then it will give us the identity matrix, right? So we successfully inserted or put this Q, although it is applied twice, but yeah, we just, they are equivalent, right? Okay, so in this case, we can just change this part, PAQ, as LU, right? So in this case, LU, and this whole part is Q. Yeah, maybe this guy is, so in this case, it can be written as a Q transpose. I mean, you guys can understand or easily prove that Q transpose or Q3, Q2, and Q1 is actually like Q1, Q2, Q3 transpose 1. So in this case, it should originally be having this transpose sign, but always this column permutation or the row permutation is always like a symmetric matrix. Okay, so if we flip them along the diagonal elements, and then it will give us the same result. And so we can just omit this part, right? And so we can conveniently write it in this form. And so LU and PAQ is the change it into LU, and then it is Q transpose X is equal to B. Okay, so let me finish the lecture maybe in a minute or two. So in this case, okay, so let me write it in this form. PA and the Q transpose X is equal to PB, right? So it's a row permute. So we understand applying P is just equivalent, because it's just a matter of changing the order of these equations, right? But in this case, suppose like we just in this case this is changed into LU and Q transpose X and PB. Okay, so in this case, this one will become our new vector X prime, for example. Okay, so let's just denote it as X prime, and then let's just obtain or solve for this X prime by just doing the two-step of this forward substitution and the backward substitution. And then what's the relationship between X prime and the Q transpose X? So it is just a Yeah, so Q is originally like yeah, Q transpose is a Q1 Q321, and then we have an vector X, which is our variable vector, right? And then Q1 was the column pivoting originally, like the changing maybe the first column and the fifth column, and then it is now multiplied on the left of the vector X, and then it is having the effect of changing the first and the fifth variable, and the second one, if it is changing the second and the fourth columns, and then when it is multiplied on the left, and then it becomes the row interchanges, and then we just change, yeah, the order of the variables that we have, right? So it's like intuitively this kind of process. I mean, so yeah, the point is, so once obtaining x prime, and then once we change their orders, and then we just recover the original yeah, variable x, and then intuitively that process is just like, where is the equation that I just wrote? Yeah, so in this case, yeah, it's just like changing it into this form, 2 or 3x2 and 2x1 is equal to -1, and negative x1 to x1 is equal to 5. And then it is like 3, 2, and -1 and 1, which we changed the columns of our matrix, right? And then we just wrote x2 and x1, right? So we basically changed the columns of the original matrix of an A, and then correspondingly we can just change the order of our variable that is associated with each column. So that is the meaning of this application of column pivoting to the linear system. I mean linear system solving. Yeah, when we want to use the complete pivoting based LU factorization. Okay, so any questions so far? So 네.
Regarding the exam, will there be asked about stuff you didn't go through here in this class?
No. It will, yeah, it will just cover, I mean, the scope will be just what I covered during the class. Any other questions? Okay, then, thank you very much.